Hello, Year 12. How are you? Everything good? Right, so yesterday I gave you two questions from past AS questions that I think are quite challenging. Certainly, when the AS students at my old school, we used to do the AS exams, and I remember them coming out and saying that these were quite tricky. So I've kept these back from you, and I want you to have a go without the mark scheme, completely fresh, as if you were, attacking it yourself. And I'm going to give you a little bit of a walkthrough video now. I'll attach the mark scheme to show my homework, and you can use that. But this is how the answers are done. It's a bit like exam technique, if you will. Haven't practiced this. This is the kind of thing I'd do on the board. But if I make a mistake, I'll own up to it, and I'm a human. Right. So here's question one. Wire probe is used to measure the rate of corrosion in a pipe carrying a corrosive liquid, water if you will. The probe is made from the same metal as the pipe, which means that the rate of corrosion in the wire is the probe is the same as the pipe. So all this is saying is, as the pipe corrodes, it rusts, then the wire will rust. And this ingenious device is designed so we can remotely check the corrosion and hence replace the pipe when it's done. So it's all context really, and hasn't got a great deal to do with the electricity within the question, but to have a context is a good thing. Makes it a bit more real world. Right, so there's the wire. The terminal here, so that's what's connected. And the wire in the unused probe has a resistance of 0.07 ohms and a length of 0.5 meters. Calculate the diameter of the wire, that's what we want, and the resistivity of the metal rho is 9.7 times 10 to the minus 8 ohm meters. Right, so there's the information. Luckily there's no tricks or traps in there in terms of prefixes, so it's a straight, it's not a straight chucking formula, but it requires a little bit more. Right, what we want is a diameter. Our resistivity formula is rho equals RA over L. You'll notice that there is no diameter, of course, but the area is linked to the diameter. So if we rearrange, A equals rho L over R, which gives us 9.7 times 10 to the minus 8 times by 0.5 over R, which is 0.07. Chuck it in the old calculator. 9.7 times 10 to the minus 8, 0.5 all over 0.07, which gives us an area of 6.92857 times 10 to the minus 7, but that is area and not diameter. What we need from this then is the diameter. Now, I'm a pi r squared man, but there is another way, isn't there? But I'm a pi r squared man, which means r will equal a over pi square root. Now, if we chuck that in the calculator, then use our answer from the last question and put pi in there, then we get an answer of 4.69. so R is 4.696 times 10 to the minus 4, but that is R and not D. D is what we want. What's the relationship between D? D equals 2R. So I'm going to multiply my answer by 2, and that gives me 9.3924 times 10 to the minus 4. What significant figures should we use here? Looking at the data in the question, it's all to 2 sig figs. So I'm going to say 9.4 times 10 to the minus 4 meters. Put it in my answer box. Now I'm quite happy with that. And away we go. Right. So that's the working out for the first one. Shouldn't have thought you'd have many problems with that, if I'm honest. That is not massively difficult. It's a nice easy starter question, but you just have to remain disciplined by keeping the numbers in the calculator and whatnot. Alright, then we go on to the next question. Now we're starting to use a bit more circuitry. I'm sure you'll be well excited about that. In order to measure the resistance of the working probe, it is connected in the circuit shown. So the first thing you should always do is just have a little look at the circuit. What's going on here? We've got an EMF here of 1.5 volts, and underneath down here it does say we've got negligible internal resistance, so we can take that as 1.5 volts, more of that later. We go through an ammeter and then into a parallel circuit. At the bottom of the parallel circuit we've got R2, a fixed resistor, and a variable resistor R3. Up at the top we've got R1 and our probe. This is what the probe we just worked out the diameter of. Okay, right, so let's go to the question now. We've got an idea of what we're doing. When R3 is adjusted to a particular value, the current in the cell is 0.66 amps. Now, I'm going to actually write that on there. I find that useful to do that, because then I know what's going on. And I know that 0.66 amps will come up here, come to this junction here, and using Kirchhoff's current law, it will go up here and down here. Will it split evenly? Only if these resistances are the same as these resistances, which they're not going to be, are they? Nothing's ever that easy. Okay, right, so calculate the total resistance of the circuit. Well, the total resistance is going to be V over I, which comes from V equals IR, which gives us 1.5 over 0.66. .27 recurring, and we'll call that 2.3 ohms. Shouldn't give you that much of a problem if you've been following along with all the other questions we've done. Easy peasy. Right, next question. The resistance of R2 is 22. Now we're given data like this. I'm going to start writing that on the sheet here. We know that's 22 ohms, and the resistance of R3 is 1.2 ohms. Calculate the current in R3. Right, so using our series and parallel rules here, obviously the total resistance is 22 plus 1.2, which is 23.2. What's going to be the PD across both of these here? Well, we know if it's 1.5 there, we're 1.5 there, and 1.5 up here across A, so this is 1.5 volts, which means that the current going through R3 will be a matter of. So it's very hard to V equals IR, therefore I equals V over R. V is 1.5, R is 23.2, 1.5 over 23.2 equals syntax. What have we done on there? 1.5. Press divided over, didn't I? 0.064, and then some loads of reoccurring numbers going on there. So 0.6465, we'll put 3 sig fig, we'll go to that. 0.647. Okay. So now I can put that on my diagram, can't I? Because I know that going down this, this is too big. Going down here, we've got 0.0647 amps. 0.66 is coming in here. Now already that tells me something about the other way, and I'm going to put that on now because I'm going to do 0.66 minus the answer from the last question, which gives me 0.595 amps, because they have to split and add up to 0.66. This is where Kirchhoff's laws become very useful. Right, calculate the resistance of the probe when the resistance of R1 is 2.4 ohms. So R1, 2.4 ohms. What do we know about this? Well, if we know that 0.595 is going up here and it's going through 2.4, then we can find the potential difference across here, can't we? So V equals IR. Do it up here, you do it down the bottom, okay? V equals IR. I is 0.595. Still got that in my calculator, luckily enough. I can multiply that by 2.4. And we've got a potential drop here of 1.43 volts. Now the total PD going across the whole branch is 1.5. So now we're going to do 1.5 minus the last answer. So over the probe we've got 0.0711 volts. Right? Happy so far? Across here, that is. Now if we want, we know the current is the same going through here as going through here. So if we wanted the resistance, R equals V over I. We've got 0.0711 over 0.595 should equal should equal 0.119495. We'll get that to 2 sig figs, 0.12 ohms. Does that match up with the answer? Yes, it does. Leave it on. Therefore, all that working out would go down here, of course, and the answer would be 0.12 ohms. Right, now I'm not a massive fan of this next question. It's all about kind of relationships between. But if we look at, right, so calculate the percentage change of the diameter when its resistance increases by 1.6%. Right, now to do this we've got to think about the relationship between the diameter and resistance. And from the formula we used earlier, R equals rho L over A, which means that A is inversely proportional to R. Right, so as R goes up, as A goes up, R comes down. As A goes down, R goes up. Right, so if this resistance here, if that increases by 1.6%, then the area here will decrease by 1.6%, as long as everything else stays the same, which the length will stay the same and the resistivity will stay the same. However, as we discovered earlier, A does not equal D. D is a ratio of 4:1. So therefore, if 1.6 goes up here, then the percentage change in the diameter will therefore be 0.8%. And that's where that one comes from. It's all about ratios. Because R is squared, isn't it? Yeah. So that one will be 0.8%. What's the formula? Right, let's spin away. Pi d over 2. So area equals pi d over 2. Which means that decreases by 1.6%. This is half of that ratio there. So that's where the 0.8% comes from. It did say you can accept 1%, but I think really the 0.8 is, so it comes from that formula, less so than the pi r squared. Alright? So as r goes up by 1.6%, a must come down by 1.6%, but d is half of a. There we go. Right, the next question is real good thinker. And this is kind of the one that differentiates whether the students have really understood or if they're just completely blagging it. Right, so the voltmeter, a voltmeter, is connected at points A and B in the circuit, and R3 stays at 1.2%. So R3 here, 1.2 ohms. So explain without calculation why the reading on the voltmeter does not change with the circuit. When the cell in the circuit is replaced with another cell, the same EMF, but this time without a negligible internal resistance. Now we've got a significant internal resistance, which significant was just high. Right, so I'm going to go back to the drawing now and hopefully make a bit more sense of it. Right, so there's our circuit. First up, if the circuit changes, that is going to change, that is going to change, that is going to change. Alright, we can't help that. What does internal resistance mean? Well, that means here we have to include here an internal resistance like that, right? Now 1.5 then becomes the EMF. And we've got the external resistance out here, and now we've got this internal resistance here, R. What we would get now is a terminal PD, wouldn't we? So let's say it has got a significant internal resistance. And let's say that we lose, I don't know, I'm making up numbers here, 0.4 volts across that significant internal resistance. What would we see outside here? Well, we'd see 1.5 minus 0.4, so across here, in terms of what we would get 1.1 volts across the terminal PD, 1.1 volts. And if we've got 1.1 volts here, then we'd have 1.1 volts here, and across both of those, these would change, across both of those we'd have 1.1 volts too. Okay, so far? Well, hopefully so. These are called lost volts, if you remember from the lesson last week. Alright, lost volts. Alright? Now, what does potential difference actually mean? Potential difference, what does it mean? It means difference in potential energy at that between 2 points. Right, so difference in potential energy. So what we're saying is that the coulombs of charge gain energy as they come up here. They come round, they lose energy there, they lose energy there, they lose energy there, they lose energy there, and they come back and get some more energy. So what we're saying is if we put a voltmeter across here and here, I'll change the colour code because it's getting a bit busy. If we put a voltmeter across there and there, what we're actually looking for now is the difference of energy between there and there. Now earlier on we had 1.43 and 0.7, so it comes up here with 1.5, it loses 1.43 and then it loses the rest across there, and it'll take that point there, and across up here we haven't done the maths, but this is like 20 times bigger than that, so I don't know, the ratio probably pretty similar, and this voltmeter here would take the ratio between the two. Whatever the voltage is there gets lost again. Now if we have 1.1 volts now, does the difference between these 2 points actually change? No. the whole line that we're saying it loses there, that will fall down. There will be less energy, but they'll both fall down together. Why? Because these ratios of resistances here and here stay the same. Now that really takes an understanding on with understanding of potential difference within a circuit, which leads a bit more to the second question as well. The whole thing will drop in energy, but it will drop together, and therefore this potential difference, the difference in potential energy between these 2 points here, A and B, will stay the same, and that's where the question comes from. So we're talking about terminal PD would be lowered. So let me just write it down. I suppose you could. The terminal PD will be lowered. Because of the lost volts. But the ratio of the resistor stays the same. Stays the same. And if there's, therefore the PD, the potential difference between A and B, will stay the same too. Why doesn't the voltmeter affect it? Well, the voltmeter is, we like to think, infinite resistance, so it won't affect any the circuit at all. I mean, that's a lot of points for 2 marks. You probably only just keep it within this range here. Alright, so that's question 1. That took 20 minutes to go through talking about it. You wouldn't have that much time in the exam, and of course you would have to think about it, but hopefully you understand why I'm having to go through this one as opposed to just chucking the mark scheme out. Okay? Right. I'll do question 2 on a different video, because it's gone forever. If you haven't gone through it properly, go through it properly now. Right, see you in a bit.